Hi, hello there. Welcome to Physical Layer. On this video lecture, we will be talking about the physical layer. So the physical layer of the OSI model sits at the bottom of the stack. It is part of the network access layer of the TCP/IP model. So without the physical layer, you will not have a network. This module explains in detail the three ways to connect to the physical layer. Now for the module objective, at the end of this video lecture, you should be able to explain how physical network or physical layer protocols, services, and network media supports communications across data networks. So subtopics included on these video lectures are the purpose of the physical layer, the physical layer characteristics, copper cabling, UTP cabling, fiber-optic cabling, and wireless media. So let's start with the purpose of the physical layer. Okay, so the physical connection, whether connecting to a local printer in the home or a website in another country, before any network communications can occur, a physical connection to a local network must be established. Okay, so a physical connection can be wired connection using cable or through wireless connection using radio waves. So the type of physical connection used depends on the setup of the network. For example, in many corporate offices, employees have desktop or laptop computers that are physically connected via cable to a shared switch. So this type of setup is a wired network. So data is transmitted through a physical cable. Now, the physical layer, the OSI physical layer, provides the means to transport the bits that make up the data link layer frame across data network. So this layer accepts a complete frame from a data link layer and encodes it as a series of signals that are transmitted to the local media. The encoded bits that comprise a frame are received by either an end device or an intermediary devices on the other end. Now on this slide, you will see how data is encapsulated from one layer to another. For instance, you open a website, okay, on your browser. Now this website represents a real data, okay? So on the application layer, we call this data. Now this data will be encapsulated once it reaches the network layer or the transport layer, okay? On the transport layer, it will be appended with a header or a TCP header. Okay? Now, this TCP header and data is now what you call TCP segment. So after the encapsulation process, it will be moved downward on the network layer. Now, on the network layer, an IP header will be appended. And this PDU or protocol data unit is now what you call IP packet. Okay? So after the encapsulation, it will be moved downward on the data link layer. Okay, so we're in an Ethernet header and a trailer will be appended and we call it a frame. Okay, now this Ethernet frame will be forwarded on the physical layer on the cable and it is now in a form of bits before it will be forwarded to the workstation or to the intermediary devices. All right, so that is the encapsulation process until it reaches the physical layer. Now let's talk about the physical layer characteristics. Okay, so physical layer standards. In the previous topic, you gained a high-level overview of the physical layer and its place in a network. So this topic dives a bit deeper into the specifics of the physical layer. So this includes the components and the media used to build the network, as well as the standards that are required so that everything works together. Okay, so the protocols and operations of the upper OSI layers are performed using software designed by software engineers and computer scientists. The services and protocols in the TCP/IP suite are defined by the Internet Engineering Task Force, or the IETF. So the physical layer consists of electronic circuitry, media, and connectors developed by engineers. Therefore, it is appropriate that the standards governing this hardware are defined by relevant electrical and communications engineering organizations. So there are many different international and national organizations, regulatory government organizations, and private companies involved in establishing and maintaining physical layer standards. So for instance, the physical layer hardware, media, encoding, and signaling standards are defined and governed by these standards organizations. So this includes the ISO, or the International Organization for Standardization, okay, the Telecommunications Industry Association, Electronic Industries Associations, or the TIA-EIA. You also have the ITUT, okay, the American National Standard Institutes, or the ANSI, the Institute of Electrical and Electronics Engineers, so the National Telecommunications Regulatory Authorities, including the Federal Communication Commission, or FCC in the USA, and the European Telecommunication Standards Institute, or the ETSI. Okay? So also part of it is the ITUT, or the International Telecommunication Union. Okay? So in addition to this, there are often regional cabling standard groups, such as the Canadian Standard Associations, or the CSA, the CENELEC, or the European Committee for Electrotechnical Standardization, and GSA, or GIS, the Japanese Standards Association, which develop local specifications. All right? Okay, so let's talk about the physical components now. The physical layer standards addresses three functional areas. So these are physical components, encoding, and signaling. Okay? So physical components, the physical components are the electronic hardware devices, media, and other connectors that transmit the signals and represent the bits. Hardware components such as NICs, or the network interface cards, interfaces, and connectors, cable materials, and cable designs are all specified in the standard associated with the physical layer. Okay? So the next one is encoding. So encoding, or line encoding, is a method of converting a stream of data bits into a predefined code. Codes are grouped of bits used to provide a predictable pattern that can be recognized by both the sender and the receiver. In other words, encoding is the method or pattern used to represent data information. This is similar to how Morse code encodes a message using a series of dots and dashes. So for example, Manchester encoding represents a 0 or 0 bit by a high to low voltage transition. Okay? So from the diagram here, you can see that 0 is the transition from high going to the low. And 1 is the transition from low going to the high. Okay? So this is an example of Manchester encoding. Now, the transition occurs at the middle of each bit period. So this type of encoding is used in 10 Mbps Ethernet. Faster data rates require more complex encoding. So Manchester encoding is used in older Ethernet standards, such as the 10BASE-T. So Ethernet 100BASE-TX uses the 4B over 5B encoding, and 1000BASE-T uses 8B over 10B encoding. So the transition occurs at the middle of each bit period, as shown in the diagram here. Okay, so how about signaling? So the physical layer must generate the electrical, optical, or wireless signals that represent the 1 or 0 in the media. Okay? So the way that bits are represented is called the signaling method. So the physical layer standards must define what type of signal represents a 1 and what type of signal represents 0. So this can be as simple as change in the level of electrical signal or optical pulse. For example, a long pulse might represent a 1, whereas a short pulse might represent 0. So this is similar to signaling method used in Morse code, which may use a series of on and off tones, lights or clicks to send text over telephone wires or between chipsets. Okay? Now the figure here shows different display signaling. Okay? So in here, on the first diagram, it shows the electrical signals over copper wires. Okay? And then on this diagram here, light pulses over fiber optic cable. And in here, on the third diagram, it represents microwave signals over wireless. All right? Okay, so next is the physical layer characteristics bandwidth. Okay, so maybe you often heard the word bandwidth. What is a bandwidth? Okay, so different physical media support the transfer of bits at different rates. So data transfers is usually discussed in terms of bandwidth. Bandwidth is the capacity at which a medium can carry data. So digital bandwidth measures the amount of data that can flow from one place to another in a given amount of time. So bandwidth is typically measured in kilobits per second or kbps, or megabit per second mbps, or even gigabit per second gbps. So bandwidth is sometimes thought as the speed that bits travel. However, this is not accurate. For example, in both 10 Mbps and 100 Mbps Ethernet, the bits are sent at a speed of electricity. The difference is the number of bits that are transmitted per second. So a combination of factors determines the practical bandwidth of a network. So the properties of the physical media, the technologies chosen for signaling and detecting network signals, the physical media properties, current technologies, and the law of physics, okay, all play a role in determining the available bandwidth. Now the table shows the commonly used units of bandwidth measurement. Okay, so bit per second is in bps. So we are using the small letter b for bits, because if it is the uppercase letter B, it's bytes. Okay, so bandwidth measurement is in terms of bit per seconds. All right, so how about the bandwidth terminology? Okay, what are the terms used to measure the quality of bandwidth? So this includes latency, throughput, goodput. Okay, so these three terms are used or often describe bandwidth. Okay, let's dig into the details of the following terms. Let's start with latency. Okay, latency refers to the amount of time, including delays, for data to travel from one given point to another. In an internetwork or a network with multiple segments, throughput cannot be transferred faster than the slowest link in the path from source to destination. Okay, even if all or most of the segments have high bandwidth. So it will only take one segment in the path with low throughput to create a bottleneck in the throughput of the entire network. Okay, next is throughput. So what is a throughput? So throughput is the measure of the transfer of bits across the media over a given period of time. Okay, so due to a number of factors, throughput usually does not match the specified bandwidth in a physical layer implementations. So throughput is usually lower than the bandwidth. So there are many factors that influence throughput: the amount of traffic, the type of traffic, the latency created by the number of network devices encountered between the source and destination. So there are many online speed tests that can reveal the throughput of an internet connection. So the figure provides a sample tests from a speed test. Okay, So you've got the download speed and then the upload speed. Okay, so the throughput is not equal to the bandwidth because the throughput pertains to the actual data transfer. All right, so if you want to measure the actual speed of your internet, then you need to get the throughput, not the bandwidth. Okay, because the bandwidth is usually the difference between the highest frequency and the lowest frequency. So it's a capacity of the channel. Okay, so the next term is good put. Okay, so there is a third measurement to assess the transfer of usable data. It is known as the good put. So good put is the measure of usable data transferred over a given period of time. So good put is throughput minus traffic overhead for establishing sessions, acknowledgements, encapsulation, and retransmitted bits. So good put is always lower than throughput, which is generally lower than the bandwidth. All right. Okay, so let's talk about copper cabling now. So characteristics of a copper cabling. So copper cabling includes coaxial cable, STP, and UTP. These are all copper. So copper cabling is the most common type of cabling used in networks today. In fact, copper cabling is just one type of cable. So there are three different types of cable cabling that are each used of specific situations. So networks use copper media because it is inexpensive, easy to install, and has low resistance to electrical current. However, copper media is limited by distance and signal interference. So data is transmitted on copper cables as electrical pulses. A detector in the network interface of a destination device must receive a signal that can be successfully decoded to match the signal sent. However, the farther the signal travels, the more it deteriorates. Okay, so this is referred to as signal attenuation. For this reason, all cables media or copper media must follow strict distance limitations as specified in the guiding standards. Now, the timing and voltage, okay, of the electrical pulses also are susceptible to interference from two sources. Okay, so these two sources are the electromagnetic interference, or the EMI, and the radio frequency interference, or the RFI. Okay, so the third one is, of course, the crosstalk. Now, electromagnetic interference, or EMI, or radio frequency interference, or RFI. So EMI and RFI signals can distort and corrupt the data being carried by copper media. So potential sources of EMI and RFI includes radio waves and electromagnetic devices, such as fluorescent lights or electrical motors. Okay. So next is crosstalk. What is a crosstalk? Okay. Crosstalk is a disturbance caused by the electric or magnetic fields of a signal on one wire to the signal in an adjacent wire. So in telephone circuits, crosstalk can result in hearing part of another voice conversation from an adjacent circuit. So specifically, when an electrical current flows through a wire, it creates a small circular magnetic field around the wire, which can be picked up by the adjacent wire. So that's a crosstalk. Okay? All right. So the figure shows how data transmission can be affected by interferences. Okay? So in here, on the first diagram here, a pure digital signal is transmitted. So this is how it looked like. Okay? And then on the medium, there is an interference signal. So what happens to your signal is it gets distorted. Okay? Now the third here, the digital signal is corrupted by an interference signal. Okay? And then the fourth, the receiving computer reads a changed signal. Notice the 0 bit is now interpreted as 1 because you have the distorted signals. Okay? Now, to counter the negative effects of EMI and RFI, Some types of copper cables are wrapped in metallic shielding and require proper grounding connections. So to counter the negative effects of crosstalk, some types of copper cables have opposing circuit wires, okay, or which this pairs of twisted together. Okay, so this is for the copper cables, which effectively cancels the crosstalk. Okay, so that is why your UTP is shielded. Okay, or your UTP and STP are shielded, and it is twisted. Okay, so that is to go against crosstalk. So the susceptibility of copper cables to electrical noise or electronic noise can be limited using recommendations. So selecting the cable type or category most suited to a given network environment. So designing a cable infrastructure to avoid known and potential sources of interferences in the building structure. So using cabling techniques that include the proper handling and termination of the cables. Okay? All right. So there are three main types of copper media used in networking. All right. So you've got the commonly used unshielded twisted pair or UTP cable. Okay. You've got the shielded twisted pair or STP cable and the coaxial cable, which is already obsolete. Okay. Now take note that these cables here, this is called twisted pair. Okay. So going back to our discussion earlier, why is it twisted? It is twisted because it is a protection against crosstalk. All right. Okay. So let us discuss each of the cable in detail. Okay. So let's start with the unshielded twisted pair or UTP. So unshielded twisted pair cabling is the most common networking media. So UTP cabling terminated with RJ45 connectors is used for interconnecting network hosts with an intermediary networking devices such as switches and routers. So in LANs, UTP cable consists of 4 pairs of color-coded wires that have been twisted together and then encased in a flexible plastic sheath that protects from minor physical damage. Okay? So the twisting of wire helps protect against signal interferences from other wires. So as seen in the figure, okay, so the color codes identify the individual pairs and wires and aid in cable termination. So the numbers in the cable or in the figure identify some of the key characteristics of unshielded twisted pair. Okay, so the first one, the outer jacket, protects the copper wires from physical damage. Okay, and then second, the number 2 here, twisted pairs protect the signal from interferences like crosstalk. Okay, and the third one is a color-coded plastic insulation electrically isolates wires from each other and identifies each pair. All right. Okay, so the second type of copper cable used in network is the STP or the shielded twisted pair. So shielded twisted pair provides a better noise protection than UTP cabling. So however, compared to UTP cable, STP cable is significantly more expensive and difficult to install. So like UTP cable, STP uses an RJ45 connector. So STP cable combine the techniques of shielding to counter the EMI and RFI and wire twisting to counter crosstalk. So to gain the full benefit of shielding, STP cables are terminated with a special shielded STP data connectors. If the cable is improperly grounded, the shielded will act as an antenna and pick up unwanted signals. So the STP cable shown in the diagram uses 4 pairs of wires, each wrapped in a foil shield, which are then wrapped in an overall metallic braid or foil. Okay, so now using this diagram here, okay, so the numbers in the figure identify some key features of the shielded twisted pair. Okay, so first you've got the outer jacket, and then the second protection is the braided or foil shield, And then each pair has what you call foil shields. And each wire is, of course, twisted pairs. You've got the insulator. Okay? Alright, so the third type of cable used is coaxial cable. Okay? So coaxial cable, or coax for short, gets its name from the fact that there are two conductors that share the same axis. So as shown in the figure, coaxial cable consists of the following. So a copper conductor is used to transmit electronic signals. Okay? A layer of flexible plastic insulation surrounds the copper conductor. The insulating material is surrounded in a woven copper braid or metallic foil that acts as the second wire in the circuit and a shield for the inner conductor. The second layer or shield also reduces the amount of outside electromagnetic interference. So the entire cable is covered with a cable jacket to prevent minor physical damage. So there are different types of connectors used with coaxial cable. So the bayonet Neil Conselman, or BNC, N-type and F-type connectors are shown in the figure here. You've got the BNC connector, you've got the N-type connector, and you've got the F-type connector. Okay? Now, although UTP has been essentially replaced coaxial cable in modern Ethernet installation, the coaxial cable design is used in the following situations. Okay? So wireless installations. Coaxial cables attach antennas to wireless devices. The coaxial cable carries radio frequency energy between the antennas and the radio equipment. So that is where we use coaxial cable, okay, on wireless installations. Next is in cable internet installations. So cable service providers provide internet connectivity to their customers by replacing portions of the coaxial cable and supporting amplification elements with fiber optic cable. So however, the wiring inside the customer's premise is still coaxial cable. All right? Now, on the numbers here, on the representation, okay, so number 1 is of course the outer jacket. Okay, number 2 here is the braided copper shielding. Number 3 is the plastic insulation, and the fourth one is of course the copper conductor. Okay, so next is UTP cabling. Okay, so this is the commonly used UTP cable in a local area network. Okay, so in the previous topic, you learned a bit about unshielded twisted pair, or UTP. Okay, so because UTP cabling is the standard for use in LANs, this topic goes into detail about its advantages and limitations, and what can be done to avoid problems. So when used as a networking medium, UTP cabling consists of 4 pairs of color-coded copper wires that have been twisted together and then encased in a flexible plastic sheath. All right? So each small size can be advantageous during the installation. Now, UTP cable does not use shielding to counter the effects of EMI and RFI. So instead, cable designers have discovered other ways that they can limit the negative effect of crosstalk. Okay? So the first effect is, of course, the cancellation. So designers now pair wires in a circuit. When 2 wires in an electrical circuit are placed close together, their electromagnetic fields are the exact opposite of each other. So therefore, the 2 magnetic fields cancel each other and also cancel out any outside EMI and RFI signal. Okay? So varying the number of twists per wire, okay, so to further enhance the cancellation effect of paired circuit wires, designers vary the number of twists, okay, so for each wire in a cable. So UTP cable must follow precise specification governing how many twists or braids are permitted per meter, or 3.28 feet of cable. So notice in the figure that the orange and the white orange, this one, okay, is twisted less than blue, okay, and white blue pair. Okay, so have you noticed it? Okay, so the number of twists varies. Okay, so each colored pair is twisted a different number of times. Okay, so you don't have to just twist it. Okay, so UTP cable relies solely on the cancellation effect produced by twisted pairs. Okay, so to limit signal degradation and effectively provide self-shielding for wire pairs within the network media. Okay. All right, so next is the UTP cabling conforms to the standards established jointly by the TIA EIA. So specifically, the TIA EIA 568 stipulates the commercial cabling standards for LAN installations and is the standard most commonly used in LAN cabling environments. Okay, so some of the elements defined are as follows. So you've got the cable types, cable lengths, connector, cable termination, and methods of testing cables. Okay, so the methods or the electrical characteristics of a copper cabling are defined by the Institute of Electrical and Electronic Engineers, or IEEE. Okay, now IEEE rates UTP cabling according to its performance. So cables are placed into categories based on their ability to carry higher bandwidth rates. For example, Category 5 cable is used commonly in 100 base TX fast Ethernet installations. Okay? Other categories include Enhanced Category 5E or Cat5e, Category 6, and Category 6A. So cables in higher categories are designed and constructed to support higher data rates. So as new gigabit or gigabit speed Ethernet technologies are being developed and adopted, so Category 5E is now the minimally acceptable cable type, with Category 6 being the recommended type for the new building installations. Okay? So the figure shows three categories of UTP cables. So you've got Cat3, Cat5 and Cat5e, and Cat6. Okay, so the figure shows three categories of UTP cable. So Category 3, which was originally used for voice communication over voice lines, but later used for data transmission. Okay? The next one is the Category 5 and 5E, used for data transmission. So Cat5 supports 100 Mbps and Cat5e supports 1000 Mbps. So Category 6 has an added separator between each wire. Okay? So if you will observe here, this is almost similar to that of the STP. So each pair of wires has what you call an insulation or separator. Okay, so Category 6 has an added separator between each wire pair to support higher speeds. So Category 6 supports up to 10 Gbps. Okay, so Category 7 also supports 10 Gbps and Category 8 supports 40 Gbps. So some manufacturers are making cables exceeding the TIA EIA Category 6A specification and refer to this as Category 7. Okay, so let's talk about different connectors used on UTP. Okay, so UTP cable is usually terminated with an RJ45 connector here. Okay, so the TIA EIA 568 standard describes the wire color codes to pin assignment or pinouts for Ethernet cables. Okay, so as shown in the figure, the RJ45 connector is the male component crimped at the end of each of the cable. Okay, so next is you've got the RJ45 UTP plugs. Okay, so this socket shown in the figure is the female. Okay, this is the female component of the network device. So wall, cubicle, partition outlet, or patch panel. So when terminated, okay, so it should be terminated properly. So when terminated improperly, each cable is potential source of physical layer performance degradation. Okay, so the next one is the RJ45 sockets. Okay, Now, this figure or the figure shows an example of badly terminated UTP cable. Okay, so this is a poorly terminated UTP cable. Try to look at and observe the installation of the RJ45 connector here. Okay, so this bad connector has wires that are exposed, okay, and twisted and not entirely covered by the sheath. All right, so a properly terminated UTP cable, okay, looks like this. It is a good connector with wires that are untwisted only to the extent necessary to attach to the connector. Okay, so a properly terminated UTP cable is a requirement for a good networks. Okay, so improper cable termination can impact transmission performance, and that would lead to performance degradation. All right. Okay, so next is the color combinations. Okay, so for the UTP cable, so straight through and crossover UTP cables. So different situation may require UTP cables to be wired according to different wiring conventions. So this means that the individual wires in the cable have to be connected in different orders to different sets of pins in the RJ45 connectors. So the following are the main cable types that are obtained by using specific wiring conventions. So first, you've got an Ethernet straight through. So the most common type of networking cable. So it is commonly used to interconnect a host to a switch and a switch to a router. So that is an Ethernet straight through. And this is based on the standards T568A or T568B. Okay, so the 568A has these color combinations. Okay, so you've got white, green, green, white, orange, blue, white, blue, orange, white, brown, and then brown. Now, commonly used is the 568B standard. Okay, so we have the white, orange, orange, white, green, blue, white, blue, green, white, brown, brown. Okay, so when you have this on both ends, this is an Ethernet straight-through cable, and this is applicable to host to network device. All right, so the next one is the Ethernet crossover, or commonly known as the crossover cable. Okay, so a cable used to interconnect similar devices. For example, so to connect a switch to another switch, a host to another host, or a router to another router, we are using the Ethernet crossover. So one end is using 568A and the other end is using the T568B. Okay? Okay, so the last type is a rollover. Okay? So a rollover cable is a Cisco proprietary cable. So it is used to connect a workstation to a router or switch console port. So using a crossover or straight-through cable incorrectly between devices may not damage the devices, but connectivity and communications between the devices will not take place. Okay, so this is a common error, and checking that the device connections are correct should be the first troubleshooting action if connectivity is not achieved. All right, so next is fiber optic cabling. So as you have learned, fiber optic cabling is the other type of cabling used in networks. Okay, so but fiber optic cabling has certain properties that make it the best option in certain situations, so which you will discover on this topic. Okay, so fiber optic or optical fiber cable transmits data over longer distances and at higher bandwidths than any other networking media. So unlike copper wires, fiber optic cable can transmit signals less attenuation and is completely immune to AMI and RFI. Optical fiber is flexible but extremely thin. Transparent strand of a very pure glass, not much bigger than a human hair. Bits are encoded on the fiber as light impulses. So the fiber optic cable acts as a waveguide or light pipe to transmit light between two ends with minimal loss of signal. So as an analogy, consider an empty paper towel roll with the inside coated like a mirror. So it is 1,000 meters in length, and a small laser pointer is used to send Morse code signals at the speed of light. So essentially, that is how a fiber optic cable operates, except that it is smaller in diameter and uses sophisticated light technologies. So fiber optic cables are broadly classified into two types. So you've got a single mode fiber and a multi-mode fiber. Okay? So the single mode fiber consists of a very small core and uses expensive laser technology to send a single ray of light, as shown in the figure here. So SMF, or the single mode fiber, is popular in long distance situations, spanning hundreds of kilometers, such as those required in long-haul telephony and cable TV applications. Multi-mode fiber, or MMF, consists of a large core and uses LED emitters to send light pulses. So specifically, light from a LED enters the multi-mode fiber at different angles, as shown in the diagram. Okay? So, popular in LANs because they can be powered by low-cost LEDs. So it provides bandwidth up to 10 Gbps over link lengths of up to 550 meters. Okay? So one of the highlighted differences between the multi-mode fiber and the single-mode fiber is the amount of dispersion. So dispersion refers to the spread out of light pulses over time. So increased dispersion means increased loss of signal strength. The multi-mode fiber has a greater dispersion than the single-mode fiber. That is why the multi-mode fiber can only travel up to 500 meters before signal loss. Okay? Alright. So how about the fiber optic cabling usage? So fiber optic cabling is now being used in 4 types of industry. Okay? So you've got the enterprise networks, so used for backbone cabling applications and interconnecting infrastructure devices. So the next one is the fiber to the home, or FTTH. So used to provide an always-on broadband services to homes and small businesses. So if you are subscribed to any of the ISP that is offering fiber or fiber to the home, so you are using fiber optic on it. Okay? So next is long-haul networks. So used by service providers to connect countries and cities. And the last one is submarine cable networks. So used to provide reliable high-speed, high-capacity solutions capable of surviving in a harsh undersea environments at up to a transoceanic distances. Alright? So search the internet for submarine cables telegraphy map to view various maps online. So our focus in this course is the use of fiber within the enterprise. Alright? Now, same with UTP cable. So fiber optic has different connectors also. Okay? So an optical fiber connector terminates the end of the optical fiber. A variety of optical fiber connectors are available. So the main difference among the types of connectors are dimensions and methods of coupling. So businesses decide on the types of connectors that will be used. So based on their equipment, note that some switches and routers have ports that support fiber optic connectors through a small form factors. Okay? So we call it the SFP transceiver, or the small form factor pluggable. Okay? So you can search the internet for various types of small form factor pluggable, or SFPs. Okay? So the first connector is the ST connector, or the straight tip connector. So ST connectors were one of the first connector types used. So the connector locks securely with a twist on and twist-off bayonet-style mechanism. The next one is the SC connectors. So the SC connectors are sometimes referred to as the square connector or standard connector. They are widely adopted LAN and WAN connector that uses a push-pull mechanism to ensure positive insertion. So this connector type is used with multi-mode and single-mode fiber. So this is also being used by your ISP. Okay, so commonly, they are using this SC connector. You go ahead and check if you are connected to the fiber to the home. Okay, so the next one is the LC or the lucent connector, simplex connectors. So LC simplex connectors are a smaller version of the SC connector. So these are sometimes called LIL or local connectors and are quickly growing in popularity due to their smaller size. Okay, so a duplex multi-mode LC connector is similar to LC simplex connector but uses a duplex connector. Okay, so until recently, light could only travel in one direction over the optical fiber. So two fibers were required to support the full duplex operation. So therefore, fiber optic patch cables bundle together two optical fiber cables and terminate them with a pair of standard single fiber connectors. So some fiber connectors accept both the transmitting and receiving fibers in a single connector, known as duplex connector. So that is shown in the duplex multi-mode LC connector in the figure. Okay. Now BX standards such as 100 base BX use different wavelengths for sending and receiving over a single fiber. All right. Next is the fiber patch cords. Okay. So fiber patch cords are required for interconnecting infrastructure devices. So the use of color distinguishes between a single mode and a multi-mode patch cords. So a yellow jacket is for the single mode fiber and an orange or aqua for the multi-mode fiber cables. So take note that fiber cables should be protected with a small plastic cap when not in use. All right. Next. Now let us compare fiber and copper. Okay. So there are many advantages to using fiber optic cable compared to copper cables. So the table highlights some of the differences. So at present, in most enterprise environments, optical fiber is primarily used as backbone cabling for high traffic, point-to-point connections between data distribution facilities. So it is used for interconnection of buildings in multi-building campuses. So because fiber optic cables do not conduct electricity and have a low signal loss, they are all well suited for these uses. Okay? Now, let's talk about wireless media. Now, let's talk about the properties of wireless media. So you may be taking this course using a tablet or smartphone. This is only possible due to wireless media. So which is the third way to connect to the physical layer. Okay? So wireless media carry electromagnetic signals that represents the binary digits of data communications using radio or microwave frequencies. So wireless media provides the greatest mobility options of all media. And the number of wireless enabled devices continues to increase. So wireless is now the primary way users connect to home and enterprise networks. These are some of the limitations of wireless. You've got the coverage area. So wireless data communication technologies work well in open environments. However, certain construction materials used in buildings and structures and the local terrain will limit the effective coverage. All right. So next is interference. So wireless is susceptible to interferences and can be disrupted by a common devices such as household cordless phones, some types of fluorescent lights, microwave ovens, and other wireless communications. So the next limitation is security. So wireless communication coverage requires no access to physical strand of media. So therefore, devices and users not authorized for access to the network can gain access to the transmission. So network security is a major component of wireless network administration. Okay, so the last one is a shared medium. So wireless LANs operate in half duplex, which means only one device can send or receive at a time. So the wireless medium is shared amongst all wireless users. So many users accessing the wireless LAN simultaneously results in reduced bandwidth for each user. So although wireless is increasing in popularity for desktop connectivity, copper and fiber cable are the most popular physical layer media. Okay? Alright, so let's talk about the types of wireless media. So the IEEE and telecommunications industry standards for wireless data communications cover both the data link and physical layers. In each of these standards, the physical layer specifications are applied to areas that include the following. So data to radio signal encoding, frequency and power transmission. Okay, so next is the signal reception and decoding requirements, and antenna design and construction. All right, so these are the wireless standards. You've got the Wi-Fi, wireless LAN, okay? And then this is 802.11, okay? You've got the Bluetooth for 802.15, WiMAX 802.16, okay? And you've got the Zigbee 802.15.4. All right, so let's start with the Wi-Fi, okay, or the IEEE 802.11. So wireless LAN or WLAN technology, so commonly referred to as Wi-Fi. So wireless LAN uses a contention-based protocol known as the Carrier Sense Multiple Access Collision Avoidance or CSMACA. The wireless NIC must first listen before transmitting to data or to determine if the radio channel is clear. So if another wireless device is transmitting, then the NIC must wait until the channel is clear. So Wi-Fi is a trademark of the Wi-Fi Alliance. So Wi-Fi is used with certified wireless LAN devices based on the IEEE 802.11 standards. So the next one is Bluetooth, okay, or 802.15. This is a wireless personal area network or WPAN standard, commonly known as Bluetooth. It uses a device pairing process to communicate over distances from 1 to 100 meters. WiMAX or the IEEE 802.16, commonly known as the Worldwide Interoperability for Microwave Access or WiMAX. So this wireless standard uses a point-to-multipoint topology to provide wireless broadband access. And the last one is Zigbee, okay, 802.15.4. Zigbee is a specification used for low data rate, low power communications. It is intended for applications that require short range, low data rates, and long battery life. So Zigbee is typically used for industrial and Internet of Things or IoT environments, such as wireless light switches and medical device data collection. Okay? So take note that other wireless technologies such as cellular and satellite communications can also provide data network connectivity. So however, these wireless technologies are out of the scope of this module. Alright? Okay, so let's talk about the wireless LAN. A common wireless LAN data implementation is enabling devices to connect wirelessly via LAN. So in general, a wireless LAN requires the following network devices. So first, we need a wireless access point. So this concentrates the wireless signals from users and connect to the existing copper-based network infrastructure, such as the Ethernet. So home and small business wireless routers integrate the functions of a router, switch, and access point into one device. Okay? So the wireless NIC adapter is also a component needed to connect to the wireless LAN. So the wireless NIC adapter, this provide wireless communication capability to network hosts. So as the technology has developed, a number of wireless LAN Ethernet-based standards has emerged. So when purchasing a wireless devices, ensure compatibility and interoperability. The benefits of wireless data communication technologies are evident, especially the savings on costly premise wiring and the convenience of host mobility. So network administrators must develop and apply stringent security policies and processes to protect wireless LAN from unauthorized access and damage.